Just on one more application example on page 85. So the equation A of t equals 6,000 times e raised to the 0.05t gives the balance after t years of an initial investment of $6,000, which pays 5% compounded continuously. Nice. They want us to find the formula for A of t, dA dt. So what do they want you to do? They want you to find the derivative of A with respect to t, okay? So simply, they want you to find A prime, okay? So let's find A prime of t. We have to use the chain rule, right? When you use the chain rule, that exponent of 0.05t will give you 0.05, right? So the constant of 0.05, you need to multiply this by the 6,000 when it comes down. So get your calculator and do 6,000 times 0.05. When you multiply them, you will get 300. So 300 is the new coefficient you need for this exponential term. But don't you change anything about that exponential term. So keep that exactly the same. Write down e to the negative, 0.05t. So, okay. All right, that's the formula. We found it. So this is the formula that will give us how fast our money is growing given a year t, okay? So when they ask for a prime of 8, yay! After 8 years, how fast is our money growing? We're going to plug in 8 into that function. And for this, we're going to need a calculator. I already know the answer better come out to be positive because we're talking about growth of our money, okay? So 300 times e to the 0.05 times 8th power. That comes out to be $447.55 per year, okay? That's how fast our money is growing after 8 years. Or I should say at 8 years, okay? That is the instantaneous rate of change of our account balance at 8 years, okay? That's how fast it is increasing. I'll say increasing. You know what I mean? If it comes out to be negative, then our money is going down, but our money is growing by this amount per year at 8-year mark, okay? And you know it's gonna go even faster. It's gonna grow even faster. The bigger the balance we have. So like in the future, like 80 years later, or like, you know, not that far, maybe 20 years later, this amount will even be bigger, okay? All right, let's see this. Compare the approximation of $448. Okay, so that must be the actual change to the actual change. Oh, no. I think that's what they did. So the compare the approximation of $448. I think they just rounded this up. They want the actual change, so let's find the actual change for them. Okay, let's try this. Okay, how would we do this? Let me think. Okay, so what is the account balance after 8 years? And what is the account balance after 9 years? So I'm planning on finding the balance after 8 years, balance after 9 years, and I'm going to subtract to see how much money grew, okay? So using that original function we got, which is 6,000 times e to the 0.05 raised to the multiplied by 8th power. So that's going to give us the balance after 8 years. If I plug in 9, keeping everything except that 9, I'm going to get a bigger amount for the balance after 9 years. So you see what I'm doing here, right? I'm trying to find how much money grew by actually plugging these into the function. So take a look. 6,000, using calculator now, 6,000 times e to the 0.05 times 9. So that's the balance after 9 years. That's good. Now, the balance after 8 years is that amount. So let me write this down. So 89.51, that's after 8 years. 94 $10 after 9 years. Okay, So what I want to know is the difference between these amounts, okay? I'll subtract 9410 minus 8951. Look at that. The actual change is equal to, what I did was I subtracted these two numbers. 459, so approximately $460. So the actual change is a little more than what we approximated, but we can see these two numbers are pretty close. Pretty close. I think you may have to subtract to figure out the actual difference on your homework though. So you may take like 459, the actual change number, minus the approximation, and get that 459 minus 448, and get there's like an $11 difference, okay, from the approximation to the actual change.